Today we're going to do class XS12, which is about the duration and the convexity. This chapter is close related with the previous exercise, practice 11. Well, practice 11 was based on bound valuation, and this chapter is an upgrade and focus on the bound duration and the convexity. All right, and for the details, you can read the textbook. In particular, you can go to the PowerPoints for chapter 12 and chapter 13. Right here, for today's practice, I want you to first start looking at this chart. So this chart is a yield curve for a bond. So you can see the vertical axis is the price and the horizontal axis is the yield to maturity. You can call the yield to maturity as the interest rate. So when the interest rate gets higher, the price will get lower. And we know that bond is a fixed income investment. So that means you receive fixed amount of cash flows for the coupons and the face value. And if you put more discount to the same cash flows, then the present value, which is the price, would be lower. So that's the general trend. It's a downward sloping curve or an inverse relationship between price and yield. All right, so you can see that the duration here is basically a given point. It's an indicator of a sensitivity at a given point on the curve. This blue curve have a lot of points, and let's see it right here. You get a point Y star, and it has a corresponding price of P star. All right, so at this point, you can draw a straight line that has only one tangent point with the curve. So this slope of this line is the bound duration. So that basically is showing you if at this point, if the bond yield drop by a certain percent, then the bond price would increase by a certain percent. And vice versa, if the yield increase by a certain percent, then the bond price would drop by a certain percent. So that's a sensitivity measure. The slope of this line at this point, all right, would be the duration. And the convexity further considers the curveness of this curve. So you can see the curve is not a straight line, it actually bent over, and we call this shape of a curve as convexity. Okay, convexity. So if you have a convex curve, then that means you need to consider the level of a bent over for the curves here and the curve right here. And then you need to perform your calculation accordingly. So why do we need both duration and convexity? So essentially, we're trying to figure out a new bond price or the price change based on the change of yield. For example, you can see the yield started from a Y star and it goes to a Y1, goes to Y3. As you can see, the bond price keeps increasing and increasing. And we want to know, first of all, the direction of the change. Of course, that's going to be a upward sloping curve. It's right here, so you know that bond price is going to increase. And the second, we want to know not just the one direction trend indicated by this straight line, but also the bent over of the bond curve. So this amount should be also estimated based on the level of a convexity. All right. So with that being said, if you look at the formula for duration, so you can see that's a lot of data, a lot of math formulas. So that's going to be pretty monstrous and pretty hard to calculate. And not only you have the regular duration, you also have the modified duration, which is the regular duration over 1 plus interest divided by the frequency. All right, and this is how you calculate the bond price change based on the duration, and that is based on a straight line estimation. And the next one here is the calculation of a convexity, and you can see it's still a giant monstrous formula, and if you put things in a table, it's gonna look like this. It's gonna look like this. So in this class exercise, I just show you how to calculate the convexity and the duration based on the textbook examples. All right, so let's get started. Looking at bond A and bond B, so this is bond A and this part is bond B, and I have laid out all the years from year 1 to year 10, so clearly both bonds are 10-year-old bonds, and you will see that the cash flows generated here is a $40 coupon for each year, and then at the very last year you receive not only the $40 coupon but also the $1,000 face value. And for the next bond you receive $80 instead of $40 for each year, and then at the end you receive an additional $1,000 face value. Okay, so the yield to maturity at the old level is 8%. So that will be the Y star in the PowerPoint, okay, of the chapter. All right, so the first thing I'm going to do is to discount each of the cash flows based on the 8% yield to maturity. All right, and then you get the present value of all the cash flows, and make sure the exponent is the year number. So let me just drag it all the way down, okay? And then you're gonna add up all these present values to get the bond price today. So the bond price today is the present value of all the future cash flows, including coupons and face value generated by this bond. And you're gonna do the same thing for the second bond. So cash flow divided by 1 plus 8% raised to the power of, 8% raised to the power of the year number. All right, drag it down, and then for the last one, I'm going to add them up. So just add them up. So $1,000 is the bond price. And this is not a coincidence. So you should know that if the coupon rate is 8%, that gives the $80 coupon each year, and your discount rate, which is yield to maturity, is 8% as well. So when coupon rate and yield to maturity is the same, then the bond price should be exactly 1,000. All right, so to calculate the duration, this is something new. You need to get the percentage of each present value. All right, so you will need to use each present value divided by the total, and make sure you lock the total denominator. All right, and then you just drag it all the way down. Okay, and I don't mind you to drag just one cell further because it's the finalized bond price. And then you will need to use this percentage, okay? We only need to calculate up to the point of year 10, but not year 11 or any further years. And then you need to get the time value weighted time. So you will need to multiply this percentage. So that's the value weights, okay, 5%, 4% based on this present values. And then the subject here is actually called time. So you're gonna multiply this by year number. And then you drag it down. All right, so the last thing is to sum them up to get the duration. And this is 8.12, so that's called Macaulay duration. So 8.12. And what is the format for this 8.12 number? So you can just right click on it. All right, format cells, and you can do customer. All right, and then you can just put years. That's right, the unit of measurements for duration is number of years. Okay, so that means If the yield to maturity increased by 1%, the bond price would increase by 8.12, and we just use the number of years to express that duration. All right, and I'm gonna repeat doing that for the next one. Okay, each value divided by the total. Oops. And make sure the total is locked before you drag it down. All right, and then you can use each value weight multiplied by the year number. Okay, then drag it down, and then the summation of this will be the Macaulay duration, which measures the sensitivity of a bond price to the change of yield to maturity. Okay, so 7.225, and it should be 7.25 years. Okay, and then the whole thing, put a border here to make it look nicer. The next thing we want to do is to solve for the modified duration. So it's pretty easy. You just use 8.12 and the duration we have solved, divided by 1 plus the original yield to maturity. Okay, and then hit F4 to lock it, and that's basically it. And for the next one, you're going to use the solved Macaulay duration divided by 1 plus the 8%, okay, for bond B, and then you hit F4. That's it. All right, so the duration effect is changed. It's already solved. So the next thing is let's go for the price change. All right, for the price changes of both bonds. So let's see, both of the bond had a yield to maturity of 8% here, and we're going to imply a new yield to maturity, which is 7.5%. As you can see, if I use the new yield to maturity minus the old, then that's the negative 0.5% change in yield to maturity. And then the old price, okay, you can use the present value function, and then you have the rate and the number of periods 10, the payment is 40, and the future value is 1,000. All right, and that's the price here. Okay, so and that's consistent with the price you got here. And for the next one, it's gonna be the same, except that you're gonna change the yield to maturity to the next column, and the old price, the coupon should be $80 per year. All right, and then for the new prices, you just drag it all the way down. Okay, so you're gonna use the new yield to maturity. Okay, so that's going to be the new price, and then you solve for the change of a price. So the change of price is the new one minus the old one. Okay, so the price got increased, so the change of price is a positive, and then you get a percentage change of a price, and you're going to use the old price as the denominator. That's the benchmark. So you can see the percent change of price is about there. All right, and then I'm going to use the modified duration, okay, as it was solved there and here. Okay, and for the duration effect, I'm going to use the change of yield to maturity, okay, times the duration, and make sure the effect is positive, not negative, because the change from there's an inverse relationship between bond price and yield to maturity. And don't forget, you need to multiply the whole thing by the old price. All right, so that's the original start for the price change. And after you hit enter, then that's going to be the duration effect. And then I'm going to drag it all the way here. As you can see, the actual price change is in this row, and the duration effect is close but not exactly the same. If we get back to this curve, this diagram, you can see that the duration effect is the amount of change predicted by the straight line, which is tangent with the bound curve at the start point. You can see Y star, P star, the original yield to maturity, the original price level of the bond. And if we use the straight line to make the prediction, and you can see that's not exactly where the bound curve is, and there is still a gap between the straight line and the curve, and that can be corrected. And this is actually an error in estimating the price based on modified duration only, and this error can be filled in by estimating convexity. And convexity basically indicates how curved this bound curve is, and in geography we call that shape convexity. So how exactly do we quantify this measurement? So first of all, we need to create a column. It's called a time squared plus time. So we just use the year number here, raised to the power of 2 plus the number of year, okay? And then I just drag it all the way down. And then this one, time squared plus time. Alright, and then I drag it down. So for the convexity measure, I'm going to use the present value of the cash flow multiplied by this time factor. Drag it down. And then time factor times the present value of the cash flows. And then drag it down. Alright, and then I'm going to need to make a summation of all this cash flows. They look pretty big. Alright, so that's $70,000 for bond B. For bond A, let's see, it's roughly $60,000. Okay. Alright, so after you get the summation, we just follow the PowerPoint, actually the textbook, to get the convexity. So this is the time squared plus time, the time factor multiplied by the present value of each time or each year, and then you need to multiply by 1 plus 1 over 1 plus interest squared, and then divide by the price. So let me just do the calculation here. So after you get a summation of everything, it needs to be divided by 1 plus the 8% squared, then divided by the bond price today. Okay, so that's the convexity. And I'm going to do this for bond B. So you get the whole big chunk of summation divided by 1 plus 8% raised to the power of 2 divided by the bond price. Okay, so you have solved for the convexity, and let me just fill it in for bond A and then for bond B. Okay, so how exactly do you get the convexity effect? And you will see this is what we calculated, and that is correct. And the convexity effect is half times convexity times the change of yield to maturity squared plus P. All right, so let me just copy this to my PowerPoint so I don't keep forgetting it. All right, so what you see here is 2 parts. This part is the duration effect, which is negative modified duration times the change of yield to maturity times the price. Okay, and this part is the convexity effect, which is a half times the convexity times the change of interest squared times the price. All right, so let's do it. So first of all, I'm going to do half times the convexity, and then multiplied by the change of yield to maturity squared. Okay, and then multiplied by the original price, the old price. Okay, and that's the second portion of a price change. And then I'm going to drag it for the second bond, and then I'm going to add them all up. Okay, duration effect plus convexity effect. As you can see, this arrow is corrected, so this is the arrow I was talking about. This portion, the arrow between the actual price indicated by the curve and the predictor indicated by the straight line, and this is the convexity portion of the price change. All right, so after I have applied convexity adjustment, the total effect is right here. Okay, which is much more close to the actual change of a price. So this is how we use duration and convexity to predict the price change due to the change of interest rate.